So the next speaker is Swaraj Dash from the University of Oxford, who's going to talk about a monad for point processes.
Hi, is that fine? Is everything visible?
Yeah.
Okay. Yeah. Hi, I'm Swaraj, and I'm going to talk about ongoing work with Sam Staton on a monad for point processes. I'll start with talking about what point processes are, and I'll describe our motivation for this work. Then I'll briefly detail how exactly we construct the point process monad. And then for the rest of the talk, I'll use this monad to compositionally construct some interesting point processes. And I'll conclude with rederiving a classical result in probability theory in our setting. This result is called Wald's lemma. So let me start. A point process is simply a random multiset or a bag of points given some space X. So so a draw from a point process on some space X is going to be some multiset of, or some bag of points. Every time you draw a value from this point process, you'll get some bag of points. And they're quite useful. They're used to model things in astronomy, such as star clusters, ecology, like tree structures, image processing, and telecommunications, such as queuing theory, and things like that. So a more concrete example of a point process is this point process on the unit square, where I show 4 draws for this point process. And in each draw, we have a random scattering of points. The number of points in each draw is, it's not a constant number. It can be, it's a random number. And in a point process, each region of this unit square gives us a random variable which describes the random number of points in this region. I said point processes are random bags, and we can see that more clearly in this example on the naturals. So here's a point process where on the naturals, here are 4 draws from a point process on the naturals. And as you can see in the 3rd and 4th draws, you have overlapping points as well. So the motivation for this work, it comes from wanting to study a language called BLOG, which is short for Bayesian logic. This is a probabilistic programming language from UC Berkeley, where although they haven't described it like this, you can define probability distributions on bags of points, just like how point processes are defined. More precisely, or specifically, they define distributions over possible worlds with an unknown number of objects. And there are 2 things that interested us. Firstly, yeah, you can assign probability distributions to the number of objects in a set. And secondly, they use set comprehension notation to construct or describe these distributions or programs. This made us think of monad comprehension notation, and we decided to consider a semantics blog where, in terms of point processes. This work is done in the world of measure theory, so I want to give a brief, quick introduction to it. Given some set X, we consider sigma algebras on this set X, which is a family of subsets which is closed under complements and countable unions. And pairing X with its sigma algebra gives you a measurable space. So measure is then a function from these measurable sets in sigma X to the extended reals, such that if you have countable collections of disjoint sets, then the measure of that collection is the sum of the individual measures of the sets. And a probability measure maps values from the sigma algebra to the unit interval between 0 and 1. And in particular, the measure of the whole set is equal to 1. So as I said before, a point process is a random bag of points in some measurable space X. In other words, it's a probability distribution on bags of points. So if X is some measurable space, then we consider two monads here. Firstly, the Giry monad, which gives you the space of all probability measures on X. And we consider the bag monad, which gives us all the bags on X. So here we consider proper bags as objects, but each bag can be represented as an integer valued measure, which maps to each element its multiplicity, or natural number valued measures, in fact. By composing G with B, we get that point processes on X, or GB of X is actually the space of point processes on X. So all the elements inside GBX are point processes. Now, G and B are both monads, but it's well known that the composition of two monads doesn't necessarily give us a monad. To show that GB is a monad, we need to construct a distributive law which maps BGX to GBX, and we need to show that it satisfies a bunch of extra conditions. Once we have this L, we can use L to swap the BG for the join to a GB and then do the individual joins to get a morphism from GB, GBX to GBX. So in our work, we've shown, we defined such an L and we've proved that it satisfies all those conditions. That was most of our work. Keimel and Plotkin have shown such a distributive law to hold in set in the category of sets. In our work, we extend this to the category of measurable spaces, which makes it a little more involved. So for completeness, here's our distributive law. I won't be going into much detail, but briefly, the distributive law maps bags of probability measures on X to a probability measure on bags of X. So given some bag of probability measures on X, we need to provide an element in GBX. Now, GBX is a mapping from sigma BX to a certain probability, to a certain number between 0 and 1. And this element in sigma BX, W, is essentially a region in X along with a number. And the probability, and so given some bag of probability measures in X, you give it a region and some number, and you ask, what's the probability of, if you sample a value from each of these new i's, what's the probability that k of those points lie inside this region? We've implemented, so in the rest of this talk, I have a couple of figures, and we've simulated these figures by writing an implementation in Haskell where we used the list transformer to do this distribution. So the list transformer we use as our monad for bags. It's more illustrative to talk about our monad with examples. So the unit for the GB monad, which you get just by composing the units for the G and B, is the following. Given some point X, eta, some point in capital X, eta of that point is just the point process which deterministically always returns that one point at that fixed location. So if we have the natural numbers, then eta of 4 is this point process which deterministically all the draws will be one copy of the point at 4 and nothing more. The bind is more interesting. The bind, considering or looking at monads using the unit and bind is a more common thing in computer science because it's quite useful for programming. But this is, the bind can be defined in terms of the join or the monad multiplication, and it's similar to the Kleisli composition. So given a point process P in GBX and a function which maps points in X to point processes in Y, we can construct a final point process in GBY, or a point process on Y, by as the following simulation. So to draw a value from this overall P bind F point process, you draw a bag of points from P, and then for each of these points, which is an X, you can apply F to these points to draw a new bag of points in Y. And then you can return the union of all those points with a multiplicity respecting union of all these points in Y to result in a final bag of points in Y. And so really, if you have some algorithm for simulating a point process, then it can very nicely be written down using our bind, which is quite cool and quite convenient. So let me talk about some examples of point processes that we can construct. Firstly, let's start with just simple probability distributions. A compound Poisson distribution is a random variable. So Y, a random variable Y, is compound Poisson distributed if it's the sum of some if it's the sum of a random it's the sum of random variables, but the sum is also a random number. So it's the random sum of random variables. Now we can encode probability distributions on the naturals as point processes on our unit type, which contains just a single value, star. This is because we can identify, or the bag, or the space of bags on the unit point, on the unit type, is isomorphic to the natural numbers. You either have the bag with 1 point, or 2, or 3, or 0, and so on. And so GB of unit is isomorphic to G of n. And if you have some probability distribution with probabilities P0 to infinity, then you can construct a point process such that the probability of observing 0 points in unit is P0, the probability of observing 1 point is P1, and so on and so forth. And so let's go back to our example with the compound Poisson distribution. This distribution is, so we have n, a Poisson random variable, and each of these xn's or xi's is also a Poisson random variable with a different parameter. And we represent n using alpha 1, which is in GB unit, and each of these xi's as alpha 2. Then we can define comp PD as alpha 1 bind, and then you take the single point to alpha 2. What this does is it samples some number of points from alpha 1, which is this n, and then for each of those points, it samples some number of points from alpha 2. And by the end, it takes the union of all those points and returns the sum. Well, the sum because we're in unit, and so the union of points is just the sum or the length of the list. And that was our first example. The second example is the Poisson point process. This is a proper point process. So the Poisson point process is a point process with 2 extra properties. The number of points in any region, or each region, the random variable assigned to it is a Poisson random variable. And if you have 2 disjoint regions, then the random variables representing these 2 disjoint regions are independent. Poisson point processes are quite useful. A lot of things have been, they have really nice mathematical results, and other point processes can be approximated using them. So it's quite nice to be able to use our monad to simulate or to describe Poisson point processes. And this is done in the following way. Poisson point process on a computer, if you wanted to simulate a Poisson point process, you would sample some random number n, and in the region that you're considering, you uniformly distribute all these n points. And this n is Poisson distributed. So we can define this using 2 point processes. Firstly, Poisson unit, which is just the Poisson distribution as a point process, similar to how we did before. And secondly, is the unif, which is a point process on the unit square. And this point process returns only a single point in each draw, but its location is uniformly distributed. And so we can define this algorithm as a point process which samples some number of points from some Poisson number of points from first unit, and for each of those points uniformly distributes them on the unit square. And then you take the union of all those points and get your final draw. And finally, here's the most involved example. We can describe clustered point processes. Clustering is quite useful, or is a common phenomenon you see where you have processes that can spawn other processes. And here we consider the following problem or model. We have a forest on the unit square where the soil towards the top is more fertile than the soil towards the bottom. And so let's say we start out by spreading some random number of seeds, and over time those seeds will become trees and spawn more trees around them. But obviously, since the ground is more fertile up here, you'll have more trees here than you will down here. So how can we model this as a clustered point process? In this is the same figure as before, but I've marked the centers of the clusters that we consider. So I'll describe this model as having a Poisson number of clusters, which is each of these red stars. And at each cluster, and the clusters that are higher up have on average a higher number of points, and similarly for the ones near the bottom. So what we can do is we can construct, using our Poisson square program that we described earlier, we can select a bunch of points on the unit square, and then for each point we can sample some number of for each coordinate we can sample some number of trees that we need, and then using the normal point process, which takes a coordinate, we can using the normal point process, we can sample or assign new coordinates to the resultant trees. The overall program looks like the following, and this is how it works. So we start out with an empty field, and Poisson unit here returns a higher number of points on average if y is closer to 1, and a smaller number if y is closer to 0. So we start out by invoking Poisson square to get some random number of points on our field. And then for each of these points, for each of these coordinates, we call Poisson unit. And then for the number of points that we get, we run normal, which is the normal distribution centered around xy. And so we call it once around this point, and we get some number of trees. We call it again around this, and so on and so forth for each of the points that we have. And this is invoked 6 times. And then in the end, this is the draw that we get. Here's another example of a draw. So this is a potentially, or a fairly...
Are you about to wrap up? Because you're pretty much out of time.
Oh, yeah. And finally, yeah, so these are 2 draws. I guess I've run over time, but just in 1 minute. We've also shown how to go from GBX to MX, where M is the space of all arbitrary measures on X. And we've shown that this is a monad morphism. And using this, if we go back to our comp PD example, the expectation of the number of points in any region is the expectation of n times the expectation of xi. And we've shown that using our monad morphism, if we apply E, our monad morphism, to comp PD, we can actually rederive Wald's lemma in just 2 lines, and can be generalized further. But yeah, sorry for overrunning. That's the that's the end of my talk. So I've described our GB monad. I've shown that we can use it to construct interesting point processes. And I've very, very briefly shown that we can rederive Wald's lemma using our monad morphism. This work is novel because we've extended it to the world of measure theory. And to our knowledge, we're the first to relate point processes to elements of GBX. And I'd like to, in the future, use this to talk about the semantics of log and hopefully prove further results in point process theory using more compositional ways. Yeah, that's all. Thank you.
Thank you. Very interesting talk. So technically your time is over. It was never clear to me whether we're supposed to have 5 minutes of questions at the end, but maybe there's time for a quick question before I start the break. Is there a question from anyone?
Sorry, Prakash, he has 4 minutes for questions.
Oh, yes. Okay. So this goes over what the schedule says. Fine. Go ahead. 4 minutes of questions. Maybe you can tell us a tiny bit more about Wald's lemma, since we raced through it.
Thank you. So each region in a point process corresponds to the random number of points in it. And so for each region, you can also have the expectation of or the average number of points in that region. That's the intensity measure of a point process. And so the intensity measure of a point process to go from GBX to MX, what we've done is we can inject both G and B into M and M each. G is a proper subset of M, and B, each bag can be represented as a natural number valued measure.
Can I just ask about these general measures? They're not required to be sigma finite or anything?
No, no. I think not. This is just, all arbitrary measures on X. We don't need them to be sigma finite or S finite. And then you can use the join in M to get to go from MM to M. And we firstly proved that this composition, in fact, does give you the expectation or the expected number of points in a region. And then we showed again by showing lots of equations that this is a monad morphism. And so if you have in the GB monad, if you have P bind lambda X goes to Fx, then if you apply E, then you can do EP measure bind EFX. And so it distributes down. And then Wald's lemma, if you have some random number of random variables and you take their sum, then the expectation of this sum is En times EXI. And we can get that same thing by considering comp PD, which we defined before, and applying E to both sides. And then we get E alpha 1 measure bind E alpha 2. And this is just the weighted sum on one element, which is star. And so we get the product of E alpha 1 at star and E alpha 2 at star, which is Wald's lemma.
Great, thank you. So I don't see anybody with hands raised. I'll just keep an eye out. If anybody wants to ask a question, please just unmute yourself and ask. Can you also send us the slides by linking?
Yeah, should I put them on the Zulip chat?
Yeah, you could do that, but if you put them on the chat right here, I'll be able to download them now.
Oh, sure, yeah.
Anybody else questions? I guess not. Okay, so let us thank Swaraj once more. Thank you, Swaraj. That was a very nice talk.
Thank you.